So let's start with the knapsack problem. What is the knapsack problem? In the knapsack problem, like, we are provided with multiple items, their respective price, their respective value, and we are also given a limit, like the capacity of the bag. You can think of it kind of like we are provided with a bag and we are supposed to add items into the bag such that the value of the bag becomes maximum, and the total weight is less than or equal to the capacity of the bag. For example, if we take item 1 and item 2, we get a total weight of 110, which is less than maximum capacity of 130, and we get a total value of 100 plus 100, that is 200. But if we consider adding item 3, we will also have to add a weight of 300, which will exceed 130. So we are omitting item 3. So you can see this is a valuable item. So maybe this can be a watch, this can be, I don't know, rice, or this can be sugar, something of that sort. So this is the main idea between a knapsack problem. Like, you need to fill this bag with items such that you can add maximum value to this bag without exceeding the capacity of this bag. So within knapsack, or even like, there are 3 kinds of knapsack problems. So we have multiple types of knapsack problem. The first type of knapsack problem is the 0-1 knapsack problem. This is the most famous kind of knapsack problem. For this problem, we can add each element once, or we cannot add that element like 0 or 1. There is nothing in between. So like the last example we saw was 0-1 kind of knapsack problem. And then there is fractional knapsack problem. Like, you can also add fractions of an element into the sack. In the last case we saw, in the last case we added this item, so we got a total value of 200 and total weight of 110. So we still have 20 weight left, right? So we can add around 3 by 15 weight of item 3, so that the total weight becomes 130. We can add fractional weight from other items. So that is the fractional knapsack problem. Like, this is not really a dynamic programming based problem. This is more like a greedy based problem. Like, you can keep adding items, it doesn't really matter. You can keep adding items greedily, like based on the value by price, value by weight ratio they offer. And the third kind of problem is unbounded knapsack. In case of unbounded knapsack, you can add multiple instances of the same item. So like, it is kind of simple. Like, you keep on adding the item which has the most value. So like, let's say for 130 we can add 13 item 1. You see, we get a total value of, like, for 130 weight we get a total value of 1300. So let's start with the 0-1 knapsack problem. We are provided with a weight array and we are also provided with a value array. Like, these are the items: item 1, item 2, item 3, item 4. We are provided with the weight, we are also provided with the values, and we are also provided with a capacity. So for every element we can choose to add the element or ignore it. So this gives us a choice, and like I said earlier, like, when you can choose to add an element or not to add an element, this gives us a problem which is fit for recursion, and we can improve it using dynamic programming. So we will start with the recursion based approach, and then we will move on to create a matrix for memoization, which is the top down approach, and then we will develop a tabulation based approach, which is bottom up. So you cannot directly jump to this step. Like, you have to follow this step to build a robust solution and a robust understanding of what is dynamic programming and what is 0-1 knapsack. So for the recursive approach, we are provided with the items, with their weight, with their value, and with the capacity. So like, let's look at the choices we have. The first choice is, what if the weight of an element is greater than the capacity? Like, it is practically impossible to add that element because its weight is greater than the maximum capacity of the sack. so we will not add that element. Now let's say if the weight of an element is less than equals to the maximum capacity of the sack. In that case, we can choose to add that element or we can choose not to add that element. So this is called a decision tree. So like the first thing for any dynamic programming problem is trying to develop a decision tree. Once we develop a decision tree, it becomes really easy to like write down the code for the recursion, like the recursive function. So let's look at the decision tree. What happens when we add that element? The sack capacity reduces by wi, it becomes w minus wi, and the number of remaining elements, like let's say we are analyzing this element, so the weight capacity becomes 22 minus 1 equals to 21, and the number of elements that remains to be analyzed becomes 4, okay, n minus 1. And if we don't add that element, the capacity remains w, so we are not adding this element, so the capacity remains w, and but the number of elements that remains to be analyzed still remains n minus 1. So the remaining items is equals to n minus 1, sack capacity is equals to w. So like I discussed earlier, for any recursive problem, we start with the large possible call and then we move our way down to the like base case, call 0 or maybe call 1. So like this is called the top down approach. So we start from the top and we move our way down to the bottom. Okay, so similarly we will also follow this approach over here because this is a recursive problem. So if we consider checking the elements from the end of the array, we will keep reducing the value of n. So we'll start with call n and then we'll go to call n minus 1 and we will keep reducing the elements from the array. So the function will be pretty simple. Like we'll have to send the array for value, we'll have to send the array for weight, we'll also have to send the capacity that is permissible, and we'll also have to send the n, like the number of elements that remains to be checked. So this will be the function definition. And as we move to the base case, now generally any dynamic, like any recursive function has two main parts, like the function definition, followed by the function definition we have the base case, and other than that we also have the normal case, like normal recursive case. So for the base case we need to find the smallest valid input. So what do I mean by the smallest valid input? For this case, if n is equals to 0, then we have no items remaining to be checked, so there is no need to run the function anymore. Or if weight is equals to 0, so like there is no capacity left in the bag, so we cannot add any more elements, so in that case it will return 0. So this is the base case. We now know the base case, and the return type of the function will be int because we are returning the maximum value that is stored in the sack. Now, like since we have developed the base case, we need to develop the normal recursive case. So we have the elements, like I said, like we will be starting from the rightmost element. So we'll check like if the weight is less than the maximum capacity. If this is weight of the item is greater than the maximum capacity, we'll not add it. We'll check the remaining elements, n minus 1 elements, and the weight will remain w, capacity will remain w. Now if w, like capacity is greater than the weight of the element we are checking, we can choose to add that element or we can choose to reject that element. Like in case we reject that element, it will be the same thing, n will become n minus 1, which is 2 in this case, and then w will remain to be w. And if we add that element, w is equals to w minus w3 and n is equals to n minus 1. So this will be the function, this will be the code for the recursive approach. This is pretty intuitive. Like you should get a, like if you look at this code, you should be able to get an understanding of what this code means if you have followed through. So I'm explaining anyway. If wn minus 1 is greater than w, like the last element, if the weight of the last element is greater than the capacity of the sack, like we cannot add that element, so we'll return knapsack, the weight array, the value array, n minus 1 elements to be checked, which is 2 in this case, and w, the maximum capacity, which still remains to be 6. else, what can we see? Yeah, else if w n minus 1 is less than is equals to w. Like, we don't need to write this, I'm writing this for your understanding. If w n minus 1 is less than is equals to w, we will return, what will we return? We will return the maximum of both of these cases, because as the return type is int, we need the maximum value possible. So return type will be maximum knapsack weight value n minus 1 w, and knapsack weight value n minus 1 and w minus weight n minus 1. So you see what happens in this case is, like, this is this one, like, we are not adding the element, so wt val n minus 1 and w remains. This one is this case where we add the value, like we add the element, so plus val n minus 1, and then we reduce the maximum capacity of the sack by w minus weight of n minus 1. So if we look at the complete recursive code, to summarize, like, we have the main function int knapsack weight val n w. So the base case, if n double is equals to 0 and w double is equals to 0, we return 0, there is no profit. And if weight n minus 1 is less than is equals to w, we return maximum of case of weight val n minus 1 w and val n minus 1 plus weight val n minus 1 weight minus weight of n minus 1. So, and if none of this occurs, in the other case, when w of weight of n minus 1 is greater than w, in that case we return case of weight val n minus 1 and w. So this is the recursive solution. Now, since we already understand the recursive solution, let's move to the memoization based solution. So what is, like I said, like, since we already have the recursive solution, it can be easily converted into a dynamic programming solution using memoization. So idea behind memoization is that we keep on storing the resource intensive calculations that we keep on doing in the recursive calls. So, like, if we look at this recursive code, we can see that, like, over here we are passing n and w. Over here this is n minus 1, this is w. Over here this is getting converted to n minus 1 and w minus weight of n minus 1. So there are only two elements that are changing, one is n, another is w. So there are two elements that are varying. So this gives us an intuition that if we are to create a memory matrix which will store the values of the recursion, it should be against these two variables n and w, right? We can create a matrix for n and w which will store the values which we can use in every other recursive code. So that is how memoization comes. We declare an array called dp of n plus 1 and w plus 1. Like, we consider n plus 1 and w plus 1 to incorporate the base cases, which is n is equals to 0 and w is equals to 0. So like, you get the idea. Like, whenever you're doing a dynamic programming based solution, look at the variables that are changing, like the parameters that are causing variation, like weight, val, these are all constant, right? So there are only two things that are changing in the recursive function, n minus 1 and w, n and w. So we create a matrix based on n and w. So now let us look at the memoization code. Like, there are very minor changes to the recursive solution, and we get the memoization based code. What is that? Like, I have created a main function just for the sake of your understanding. Like this is the, like, I have given a value of -1 to all the array elements. Okay, to all the, like, matrix elements. I have created a matrix, like, I'll show you over here. I have created a matrix. This is the nth side and this is the W. So this varies from 0 to W. This varies from 0 to W. So the size is n plus 1 and W plus 1. And I have stored -1 in all these else, right? And we need the value of knapsack weight val W in DP. So what happens is int, like this is the recursive function, we are adding another parameter, that is int DP. We are also sending the value of this array. Okay, so this is the new code that you need to add. The first thing it will do is it will check if there is already any element, like if this is not equals to -1, we have already changed the value of the array, so there is already some valid input over here and it will return that one. So there is no need for calculating something that we have already calculated. Now in the next case, like if n equals to 0, w double is equals to 0, instead of returning the value, we will store that in this DP. Okay, same case, this was the code in recursion. Instead of returning this, we will store this. Instead of returning this, we will store this, and in the end we'll return this. So what happens is we keep on filling this array as we move forward, and in any case when we require to come back and use the same value, we can like directly use it from the array and from the matrix using this piece of code, instead of going through all of this and calculating the same thing all over again. So moving on to the final approach, which is the tabulation approach. The tabulation is a bottom-up approach, and like till now whatever we have done was top-down approach. We started from with the largest possible value and we moved our way up to the bottom of the base cases. But in tabulation we start from the base cases, like we initialize the base cases and then we move forward, and like move to the end of the array. Like this is pretty much same as memoization, like in terms of performance and in terms of complexity, time complexity. But this is an added advantage, because in some cases what happens is when we are using memoization, because of multiple function calls, it causes a function stack. But in this case there is no multiple function call and there is no function stack. Instead we use an iterative approach, so this is slightly better than memoization. So let's see what does this mean. Like we create the matrix like we created in the last case. So let us look at this particular element in the matrix. What does this mean? This means this is the maximum value when we have a sack whose maximum capacity is 3, and when we are only considering the first 2 elements of the array we are provided with. So using the similar analogy, if we end up finding the last element, which is this one, this should be our answer, because we are like considering a value weight of 5 and the maximum capacity of 5, and the total number of elements we are checking is 4, which is the given value. So this should be our answer. So we have done the recursive approach, we have also done the memoization based approach. Now for the tabulation based approach, there are a few changes we need to do to the memoization or the recursion based approach. We need to convert the base cases to initialization and the recursion to iteration. What do I mean by that? Let's see. Let's look at the function, we'll get an understanding. Like I said, like we will be creating an array in a matrix of dp n plus 1 and w plus 1. We already discussed the intuition behind creating this kind of a matrix, and why should we consider n and why should we consider w. What are the plus 1 for? They are for the base cases. So now let's say we run a 2D matrix, like two-dimensional array. Let's run 2 for loops. So what we do is, first we try to fill the base cases. So if I is equals to 0 and j is equals to 0, dpij is equals to 0. Okay? Now do you notice something over here? Instead of like in all the previous cases, all the previous codes, we have used n is equals to 0 and w is equals to 0. N is equals to 0, w is equals to 0. And suddenly now we are using I is equals to 0 and j is equals to 0. So what we are basically doing is I is varying from 0 to n, j is varying from 0 to w. We are moving from the bottom to the top. And so what iterative approach basically means is, like roughly speaking, replacing n with I and replacing j with replacing w with j in the main code. So if you follow closely, if I is equals to, more or less the code is same over from here. We are just replacing n with I and w with j. See, if I is equals to 0, j is equals to 0, dpij is equals to 0. If weight I minus 1 is less than equals to j, we are considering I minus 1 because of the indexing system. Like weight, like we are also adding another base case to the matrix 0 0. So the weight of I minus 1 less than is equals to j, which was w in the last case. dpij is equals to max of val I minus 1 plus j minus w. So through it is basically the same code. We're just returning the last element like we discussed over here. And this is basically the same approach, just we're replacing n with I, w, j. So you see, like if you can think of the recursive approach and you can just like get an understanding of how the recursion works completely, just adding 2 lines of like adding maximum 2 lines to the recursive approach gives us the memoization code. And if we want to further like improvise on that, just making very minor changes to the memoization code gives us the final tabulation based output. So if in the core of any dynamic programming problem is the recursive approach. It is nothing but enhanced recursion. So if we place like I said, like if we play if we pay close attention to the code, we can see that we are converting recursion to iterative approach by replacing n by I and w by j. So in conclusion, like let me conclude whatever we have done today. For any dynamic programming problem, we first try to think of a recursive approach. And how do we do that? By thinking of the base cases. What is the base case? The smallest valid input and the decision tree, which basically builds up the function. Then in the next step, we convert the recursion into a top-down dynamic programming by memoization. And how do we do that? By storing the values that we are already calculating in a 2D array. Cool. Like not necessarily 2D, that depends on the problem. So to create the memoization matrix, we try to think of the variable function parameters. Okay, so the variable function parameters n and w in this case gives us what should be the matrix look like. What should the matrix look like? So once we have the memoized solution, we just need to convert the recursion into an iterative approach, and we finally have our tabulation based dynamic programming solution.